UBC's Biomedical Engineering student team, and this is our submission to the NTXF Challenge of 2018. So we went for modular design, where we have one single case with all the electronics we needed, and electrodes that we made would plug into that board, and then out of that board would come out a USB cable that would plug into a PC from which you run a Python GUI and then visualize all the data, and then Python GUI would also save everything. Out of the unit itself, it has a board that we designed to regulate voltage. It would filter out the signals and amplify it with an ENA differential amplifier because it's the cheapest and most readily available one we could find. And then it would have a notch filter to filter out 60 Hz noise. So this is our Mentha board, our crown jewel. It also has a little case. It is metal so that we can shield everything from the inside, and this blade here keeps things from touching the metal inside of the case. This face over here is a different part of the case, so here we plug in reference and then 4 other pins for the 4 signals, and here we plug in the USB that will feed into the Arduino. So from the other side, here we have the Arduino. It can be screwed down in 4 different locations, and then we have ground pin of Arduino connecting down here. So down here we would have our battery pack, but I removed it to show you how it works. And here we have our input signals, and here is just a little strip to connect all of the different grounds together to avoid ground loops. So every ground is connected through here. Now through these holes in the board, the signals and grounds and everything else can connect to our actual filters. So up here we have one board with 2 filters, one here and one here. And then down we have another 2 filters, one here and one here. And these are just the cables that would connect other places, and I've just rolled them around so that you can see everything better. So if we look at just one filter in particular, here we have the input in white, as we came in from there. So we have the input in white, and then we have in green the ground, and they're both coming into the input here. And this capacitor and this resistor make a high-pass filter so that DC noise will get removed. And we need to remove DC noise because if there's too much DC noise that we are amplifying, we may saturate the ENA with that noise and not actually amplify neural signal. Now, those 2 signals that have been filtered go into the ENA here, and the ENA will amplify the difference between the 2 and output in this yellow here around 100 times amplification. Now this amplified signal will go into this notch filter over here. It looks like quite a web. It's just because we wanted to keep it as small as possible, and we're filtering out 60 Hz just so that the floating point of the Arduino won't have to hold too large a number to process and still have the actual signal that we cared about. Because otherwise, if you have a huge wave of 60 Hz noise and then the actual neural signal very tiny on top of it, your recording will kind of kill some of the tiny variations and record most of the large wave. So we wanted to make sure we're not losing that signal because we weren't sure how much the Arduino was going to collect in terms of numbers and size of the numbers. So we just wanted to be sure. Signal from the notch filter, it's coming in here from the amplified, and then coming out of the notch filter into the Arduino pins, and then from these pins, Arduino is going to read that information and send it to the PC through the USB cable. Alright, we made a battery holder, so this is our battery holder, has positive and negative, and here you would insert batteries facing up and here facing down, and then down here we had a conductive plate, so that would be ground, so we have 0, plus 6 volts and negative 6 volts. And then we place our board here. And then we would close it all together with zap straps that go through this slot and this slot down here. Now, we tested the battery and it worked fine. It's just that it turns out it couldn't supply the amount of current that we needed to be able to power all 4 inputs. So we decided to go for just a power supply during testing for now, and when we can find an adequate battery, we would feed it through there. We tried to power it through the Arduino with a voltage inverter to get positive and negative 5 volts to feed the ENA, but the power coming out of the Arduino has too much noise embedded in it, and that would translate into our signals. Now, because we were having noise issues, we didn't get to use our own electrodes, but I still wanted to show what we made. We preferred this design where you 3D print whatever electrode shape you want, and then you paint over it with silver paint. And we got this idea from a publication by this person over here, and here are our favorite designs. So first off, this is just a regular. This one is our favorite one. It is a hairpin electrode, so you connect it to your head as a regular hairpin, and then this part here, the actual electrode, will go through your hair. The quality is not so bad with this paint. It's just that because we were already having issues and troubleshooting it with noise, we prefer to remove that as an issue. So we've just been using gel electrodes.
So the pipeline is taking in data from 4 pins on the Arduino, and so then that will be read by the Arduino and printed to serial in a particular order. Then we have a Python program that reads from that serial, puts all of those 4 values in an array of size 4, and then reads data from each position in that array and plots it on a graph. And so we take that data and we first put it through a fast Fourier transform so that we can get Fourier transform. The key parts of the program are this function called read data, which will read from the serial. It will read from serial 4 times and store those 4 values in an array. And so then that array gets passed to the variables which hold the signal data for each graph. We want to maybe be able to add a start and stop button for recording. The Leo costs around $30.
And the Python?
And the Python is free.
From whatever filtering and amplification board you have, you need to make sure that it's only sending signals from 0 to 5 volts. So whatever signal you have, you can DC offset it and scale it down to make sure to fit this range, because this is this range of measurement for the Arduino board. Fair warning, the live demo today wasn't so alive. We took a lot of recordings, but we're in a building that I guess has a lot of noise today. And sometimes machines turn on and off in this engineering building, and the noise was a little bit too much and was overshadowing our signal. We have some parts that look like a decent EEG signal, so we didn't have it consistent enough that we could film the demo and talk about it while it was happening. For next time, we will try to get a good day. We have tested it before though, and a few times the signal did show, and it looked like an EEG signal. And the way that we test it is with the eyes closed test. So when you close your eyes, you should see a spike, a growing spike in the 10 to 8 hertz region, so your alpha frequency, because it goes up when your eyes are closed. And we did see that happen in some of the signals we collected. It just didn't quite happen today too clearly, unfortunately. Collarbone, I guess, is easiest. Yeah. And you know what channel 2 is?
It's a 10 hertz signal generated.
Nice.
Ooh, that's working.
It looks okay, but I usually expect to have large DC noise.
There it is.
Yeah, there we go. So we have DC noise and a peak at 10 hertz. That looks like brain. Try closing your eyes. Let's see if it goes higher. But do you have reference?
No. Did anything change?
Oh my god, there's 20 hertz.
I was closing my eyes.
Yeah.
Alpha is supposed to be.
We are Mint from UBC. Woo!
Great. That was very crisp.
Crisp, okay.
I'm gonna save that.